I am the local architectural sales manager for Garland. My name is Alex Zawicki. So I am local to all of you guys in Southern California. I also cover kind of Central Coast and then down to San Diego, as well as Arizona and Las Vegas now. So I will probably up top have my video on just right now and then come back on the video at the end to answer any questions that there might be. If you do have questions as we go, feel free to throw those in the chat so you don't forget. Jeff is going to kind of periodically monitor the chat and we'll see if there's anything super pressing. If not, I'll circle back on those at the end and we can get those answered. So to start off, as I mentioned, I'm going to head off the video real quick just to make sure we're not, having any technical difficulties or anything as we go on the presentation. So talking about Garland specifically, just to give us a little bit of a, a slight baseline so you guys know who we are. We are a full service manufacturer of primarily roofing systems. But that means not only single ply, which we of course have, we've got multi-ply, modified bitumen, we have metal standing seam systems. Genuinely every type of roofing system that's available is something that we can assist with. We also, which is what we're going to be talking about today, manufacture a full Rainscreen assembly as well as metal panel wall systems. But we kind of take the full service approach, which is what we're seeing here. That doesn't mean, we're not one of the manufacturers who is going to deliver the goods to the job site and be done. We are as involved in the entire design process from the architectural perspective as you guys will kind of allow us to be, or as you want us to be. The earlier, the better. But when that comes to existing construction, we provide full assessments of mainly the roof, as I mentioned, but we can do a full building envelope assessment, complementary, kind of provide recommendations, fitting, budget, design, aesthetics, etc. But it genuinely is a very comprehensive approach, which includes on-site installation, kind of boots on the ground from our territory sales managers across the country. So that ensures that these systems that we are issuing warranties for, 30, 35-year, 40-year roofing systems sometimes are going to be installed just the way that we have detailed them and designed them with you guys. So that we're ensuring that really for the life cycle of that roof or a rain screen or wall assembly, whatever the case might be, we are going to have a system that is not only detailed right, but installed perfectly as well. And just to give a little, I know we talked as far as what we are discussing today is going to be primarily Rainscreen, but just a quick snapshot too. And if anybody is interested after the fact, I can send you this little kind of really the whole presentation if anybody wants it, but just Garland specific stuff, just a quick snapshot of some of our services and systems. As I mentioned, mostly in the roofing kind of realm of things, but also metal. We have several wholly owned subsidiaries under the Garland envelope or Garland umbrella, I guess I could say too, that are manufacturing coatings, metal systems, traffic coatings, all sorts of things. So genuinely, all 6 sides of the building envelope we can assist with. So let's jump into today's content, mainly Rainscreen wall systems, but also how they are designed, why they are successful, just kind of as a concept, the whole Rainscreen as a principle, what that means, how you can design one effectively, where those air barrier, vapor control, and thermal control layers fall into the assembly and how they play into designing. And then we'll also kind of wrap it up towards the end with the basic kind of purpose of and function of a WUFI model, which I will touch on what that even means when we get to it. But again, as I mentioned, questions, if you have them, throw them in the chat. I'll kind of try to periodically monitor, and Jeff will as well. If not, we'll circle back to those on the end. But just very quickly, I do like to give credit where credit is due. These 2 sources we're going to pull a lot of information from today, just mainly because we are going to get into some building science kind of principles and tenets. So that's, of course, Building Science Corp is going to be cited a couple times, as is the whole building design group there. To start out, when we're talking about the facade of a building, we're not always designing with one single material for one building, right? In this case, we're looking at a couple different materials that are on the face of the building. We've got some brick and mortar, veneer on the left. We have metal panel as well. There's glazing. When you are designing with a Rainscreen system, behind all of that cladding, you're really able to provide and integrate so many different looks with one construction system and one method of construction on the same facility without compromising the protection of the actual structure and the building itself, and energy efficiency, which we'll kind of touch on when we get to a bit of the thermal control of it all and all that fun stuff. But the point is, when you're transitioning from material to material, really you have to have a well-designed wall system, very experienced manufacturers, especially within the Rainscreen assembly itself. Skilled tradesmen are a must as well. It just really ensures that the installation is intact as far as the integrity of the system is concerned, right? Another photo that is not uncommon as well, where we're just looking at genuinely transitions from, we've got metal cladding there, we've got glazing to framing, and then back to metal cladding. So the entire system behind the cladding that we're looking at and around these components, if not designed properly, can really lead to some major issues with the building envelope and its efficiency. Another example of same material on the majority of this here. We've got some glazing and some masonry down there at the bottom as well, but we've got a little bit more complex geometries, transitions from section to section. Again, really the point here is, as we're just looking at it on its face, this is all possible with the help of a well-designed and installed Rainscreen system behind that cladding. When we talk about Rainscreen systems and just kind of the principle in general, it is not a new concept by any means, but we have seen leaps and bounds in evolution of technology, products, kind of really defining the Rainscreen principle as well. But really, as a concept, back in kind of pastoral Norway in Europe, in kind of the 1700s, I think is when we can kind of really date it back to. They were using this open jointed barn technique of construction to essentially protect the harvest that was inside the barns, the livestock, etc. We have really updated that concept to evolve into what we see now as a Rainscreen, which we will see several diagrams as we go through this. But just keep in mind, as we kind of got through the 1900s into the 70s and 80s, we started to see more energy conservation initiatives and programs that really made construction a little bit more at the forefront of how we thought about how buildings are made, how we can better use and conserve the energy that the buildings use through their life cycle. And then even now too, we see, especially when it gets into like vapor control, which we will absolutely talk about in depth in just a moment, we're seeing even more sensitivity to the building envelopes in certain cases. A lot of that is due to changing in weather patterns, etc. So really the point here is not a new concept by any means, but tons of improvement and innovation in how we design Rainscreen and how we really understand building science in general. I touched on this briefly just as far as mentioning kind of what the control layers are and how air barriers and vapor barriers will fall into this. But when we are talking about a building envelope or a building enclosure, we're really looking at 4 different layers that we want to control. Primary one is going to be rain. So that's like liquid bulk water. We list that first. Code does not necessarily list rain as kind of the first control layer. Usually code will kind of dictate that the air barrier or air tightness is going to take precedent. No shade to air barriers and air tightness at all. It's absolutely important, but we tend to give a little bit of a slightly more importance to bulk water and rain just because, it's our experience that you don't really get a phone call at 3 a.m. because you have air leaking in your building, but you definitely will get one if you have rain leaking either on your walls or your roof, right? So Both are very important. And then we're also going to look at thermal control. That's where our insulation comes into play, and then vapor control and permeance as well. So these four layers, kind of, so to speak, or control layers are absolutely functioning kind of as a system, and they are all, especially when it comes to vapor, very much interconnected. And we will talk about each of these and how a Rainscreen system can really help kind of monitor and control this for a functional and efficient building envelope. But just talking about walls in general, right? We have to kind of have a couple principles that we just need to accept as truth, right? And one of those things is that there will always be a quote unquote problem with walls because there's always going to be water present in some capacity in the environment, either bulk water, snow, that will melt into liquid water, vapor, etc. But essentially, walls will leak for umpteen reasons. There are truly exponential reasons why walls will leak. But when we actually are kind of drilling down into the mechanism of leaking, it's really pretty simple. There's water, there's always going to be some sort of opening, either a hole in the wall or, some sort of area where water can get in. But that water is only able to get into our wall system because there is a differential in force or pressure between the inside of our building and the outside of our building. So our controlled environment on the inside, air conditioned, heated, what have you, and our uncontrolled environment on the outside. So really these three factors working together means that we might have a leak, or we would definitely will have a leak. But when we acknowledge this, which this slide here is really just the verbalization of what we kind of just went through, when we acknowledge that water will always be present and that it's very difficult to mitigate that by completely sealing the face of our walls, we've already kind of won half the battle here. But let's just establish that water is going to always be present. And in some cases, it can be too present, right? So these two photos here are truly true bummers, right? So we've got two different situations. The one on the top left, we have a masonry facade, but you can see we've got some pretty clear signs of those white kind of half moons. That's efflorescence, which is just a dead giveaway for moisture in the system, especially when it comes to brick. That's kind of how the water will present itself on the face of the brick. But essentially what happened here was a complete lack of coordination between the contractors and the trades who were installing each component of this building envelope. And we had the window contractor, the glazing guy, come in and terminate, quote unquote, the air barrier at the window openings, but did that incorrectly, which led to this efflorescence presenting itself truly 2 days after the brick was installed. So that's like almost worst case scenario because this is a brand new building. We had multiple trades coordinating, but not effectively. And by the time this was discovered, all of the brick was already pretty much installed for the most part. And then there's finger pointing and everybody's upset, including and especially the owner, right? So by kind of mitigating this through mid-installation inspections, which are not dictated by code, but are recommended from, high-end manufacturers of these kind of systems, you absolutely can avoid a problem like this. And then also too, you can see on the bottom right, sometimes you'll have some cladding systems that are just more prone to holding moisture than others. In this case, we had just stagnant water that kind of EIFS, those panels there, that EIFS system just was completely disintegrated and affected the structure behind the panels even too. So obviously we're going to see some true bummer scenarios, including these ones and including these photos here as well. Another masonry facade. This is actually an indoor pool, so a natatorium. When everything is installed, we're good to go. Everything looks great. Because we have a pool on the inside of the building, typically what you're going to want to do is run your HVAC or your dehumidifier kind of at the end of the day when everybody is gone. This didn't happen in this case, and it was almost immediate, kind of a few days after the pool was open for business. We see this very visible failure of the brick masonry walls on the outside there. And it can show itself in a couple different ways, depending on what the material is. In this case, we have some kind of almost plaster tile, but that plaster is serving as a coating that is also functioning almost as a vapor barrier, and it is trapping that moisture inside the actual tiles or the cladding itself, so it's not able to evaporate out. And you even see this sometimes, not quite as much anymore, although wallpaper is making a huge comeback, which is kind of fun. This is not so fun when it comes to wallpaper. This is an interior application where wallpaper, contact paper, etc., is also functioning as a true vapor barrier. So if you do have moisture that is trapped within that system, either it's coming in from the outside, heading in, coming down from the roof, there's a couple different things that could be happening here. But the point is, when you have that moisture being trapped by a vapor barrier that doesn't let it breathe, you're going to have, in this case, some actual biological growth. Air quality is poor on the interior, and also you could just have legit health problems that can come from this too. So those are extreme examples, but all of that is to say, we have to manage the moisture regardless of what system we're using, right? So when we are able to anticipate the fact that we will always have some sort of moisture present, be it vapor, rain, etc., and anticipate the fact that it will make its way into the wall cavity somehow, we can really design a system to direct the water to the drainage planes that we want it to go through. So in what we're going to talk about today, the Rainscreen system itself is, the cladding is our primary drainage plane, but we're also able to essentially, by having an air cavity in that system, create almost like a little convection system that we can see here. I love this diagram. I think it really shows the Rainscreen principle pretty perfectly. But this is exactly what we're just kind of going through right now, where we've got our structure, right? So that can be a stud wall, CMU, sheathing, etc. And then you have your insulation, which is optional, but we will get to that as well. This is our continuous exterior insulation, kind of that yellow layer there. And then between that, our insulation and the pinkish layer on the far left, we have our air cavity or our drainage cavity. That is between our cladding and our insulation or our structural wall. And you'll also see here, there's a little air cavity between the insulation and the structural wall as well. So really what we're looking at when it comes to a Rainscreen system, for our intents and purposes today, we are looking at here, this is a back drain and ventilated system, which really is primarily functioning because we do have that air cavity between the cladding and the face of our insulation. So what this is serving to do for us here is this main surface of our exterior cladding, which could be metal, could be, like a fiber cement panel. There are phenolic panels. There are several different options as far as the cladding goes. But the front face of our cladding is our primary drainage plane. That's going to account for 99% of the bulk water and will shed that water. Anything that gets into the open jointed system, which is pretty key for the drain and back ventilated option, that open jointed cladding, any water that gets past our primary drainage plane is going to evaporate out through this air cavity because we've essentially created kind of a pressurized system that is bringing in air and circulating it so that that water is encouraged to flow down and out of the system. So really the whole point is there's a couple different ways to do this, but by accounting for and preparing for the fact that there will be water in the system and designing it in such a way like this, where we have this air cavity that encourages the evaporation so that it is not affecting our structure and is not getting into our building. This is the main point of what we're doing today and what we're going to be talking about. I didn't touch on face sealed, which you can see at the left on the left-hand side. We've got different tests and different standards for each of these systems, but a face sealed system is not what we're looking at in this diagram. That diagram shows open jointed cladding. You can have a face sealed system. Face sealing is a little more difficult sometimes just because the cladding is going to expand and contract. And if you are sealing that cladding around the joints, that movement can sometimes allow for a little bit more water to get in the system than we actually want it to. But not to say it's better or for worse than what we're just talking about, but just know that we're looking at what this diagram is showing, which is that back drain and ventilated Rainscreen open joint cavity today. And this is a completed system. And I love to show this photo because, you know, just looking at it, you would honestly, in a lot of cases, never even know that there's a full Rainscreen assembly behind there. So on the left, well, in both really, we're showing zinc panels as the cladding. And on the left, you've got those kind of vertically oriented panels. We have very aligned reveals. They're kind of columns and rows stacked on top of each other. And then on the right-hand side, you've got those horizontal oriented panels with staggered joints. Zinc is a really great option. It's very long lasting for especially a high performance Rainscreen system like this. But you know, the interior leaf of the cavity wall is going to be protected essentially forever from UV, heat, impact, rotting. But we're effectively and adequately managing that moisture infiltration so we can specify something that's going to have a super long life, low maintenance, and that can function for truly decades. This diagram is another great one, and this is one of those ones that we're going to pull from one of our fave sources, Building Science Corporation. What we're looking at here is known as the perfect wall, and this was kind of the predominant method of construction that many commercial and institutional buildings were built using this kind of the almost exact detail. But this is how we used to build our buildings before our construction materials and techniques became, you know, quote unquote, advanced. But you can see here our structure is concrete. A concrete wall can take on a lot more moisture without losing structural integrity than some of the other structure members and types of structural walls that we see today. But it's also this perfect wall kind of methodology, and in practice it turns out much more expensive than what we see today, which is known as the commercial wall. So we don't have that concrete structure. We've got this uninsulated steel stud cavity, which is notable. We'll get to this in just a little bit when we talk about vapor, but remember that uninsulated cavity, that is not necessarily common. Usually you'll see a wall cavity with fiberglass batt insulation in there, which again, we will touch on that, put a pin in it, but just note it for a little bit down the road. But essentially, we still have those 4 control layers that we do in the perfect wall, excuse me, where you're accounting for your air barrier. You've got your insulation. You also will have, so that's our thermal control. Vapor is something that, again, that's its own topic we will touch on in just a bit. But we are getting essentially almost the same. It's very similar in concept. We just have altered this from the perfect wall so that it is, number one, less expensive to do, and number 2, a lot quicker. So of course, you know, we like to do everything quicker and cheaper. And now this is where we find ourselves on, as far as construction is concerned, this is extremely common. Love to show this too, just because now we're going to kind of get into each of the 4 control layers individually, but seeing them all together, this is a Rainscreen system without the cladding installed just yet. So that orange layer there, that's our air barrier, air and water barrier, AWB. There are several different kind of terms for that. Over that, we have our continuous exterior insulation, which you can kind of see staggered off to the left a little bit. And then you have your subframing, which is in this case, we have horizontal hat channels. You can have a couple different options there. You can also have a vertical assembly, depending on what your cladding will be. And then to finish it off, we would install our panels and then the glazing, which would go right kind of where you can see those openings there. But let's talk about each of them kind of individually. So starting with our air barrier. The whole purpose of an air barrier, which this slide is going to be a review for pretty much everybody in this call, but it's nice to just touch base, make sure we're all on the same page. The air barrier is essentially preventing the movement of air from our conditioned interior space and our unconditioned exterior spaces. So a lot of times, especially today, as far as construction goes and specifications go, an air barrier more often than not will also be a water or a moisture barrier. So you're going to have, that's kind of how I mentioned an air water barrier, AWB, extremely common terminology. Air and water barriers usually are the same material now. Sometimes, not always, but sometimes a vapor retarding or barrier component will be built into that as well. So again, one material, not uncommon at all, especially nowadays where you have that just one sheet that's accomplishing one, two, or all three of these functions, right? But when it comes to vapor, this is where things get a little more complex as far as the building science goes, and we have to absolutely take into account multiple other factors. But you can essentially have a vapor permeable air barrier, which is vapor open, right? Vapor is able to kind of almost freely pass through from inside to outside where that air barrier is at a different rate, which we'll touch on as well. You can have a vapor retarder, which is essentially slowing the movement of vapor from surface to surface or air, conditioned space to unconditioned space. Or you can have a full vapor barrier, which does not allow the movement of vapor between spaces at all. Again, you can have an air barrier that serves water barrier and vapor barrier purposes, but they do absolutely do distinct things. So keep that in mind as well. We kind of touched on this a little bit just in the fact that code absolutely gives kind of priority to air tightness. And for that reason, you really can't have a building that is considered too airtight. So redundancy in the air barrier is absolutely advantageous in a lot of cases. And we'll see a couple details of that, which is really highlighting kind of which situation you would want to have that in, et cetera. But air leakage is definitely, especially when you have a building that has to be not only energy efficient. We have a lot of requirements as far as, Title 24 is concerned, especially in California. Air leakage is truly intolerable. So for that reason, I love to show this design here, or this detail, I should say. This is an example of, we've got that perfect roof, or perfect wall, excuse me, again, where we have that steel, we've got a stud cavity wall on the vertical. And then on the roof here, we're showing a standing seam roofing system. We've got a couple of layers of rigid insulation, and then you have your deck. But the main thing that we are kind of pointing out here is what I just went over just briefly, where air redundancy in the air barrier, especially at your transitions from your wall to your roof, is so important. It's impossible to overstate how important it is, especially because, so we're showing this, the roof air barrier is in red, kind of on the slope up top, and then you see we transition to the wall, the vertical air barrier is in blue, and then they overlap at the top. I say this is especially important, mostly because it's very common to have a different trade or contractor who you've got one trade installing your roof, right? And one installing your wall assembly. It is very common for this transitional point from the roof to the wall to get missed, or for it to be one of those kind of gray areas where if we're not really specific in how we design this and how we specify this and how we bid this, then this could be an area where we're going to miss that transition point, and you have, instead of redundancy in the air barrier, you end up with no air barrier at a point from our wall to our roof, right? So Mid-install inspections are absolutely an important thing to consider here. And again, that's one of those things not dictated by code, but it can help you so much. If you catch that before you put your whole wall assembly on, it will save so much headache and so much money, honestly, right? So air barriers, again, we saw that kind of photo of, these are just going to be some nice photo examples of different kinds for you guys, but this is that same one that we just looked at where we had that orange air barrier already adhered. This is a sheet membrane, of course. And then you also, though, depending on what your substrate is, you can have a fluid applied air barrier as well. They are very common. They could be, as far as the sheet goes, they could be self-adhesive. You could have them mechanically attached. There's a couple options as far as that's concerned based on your substrate and your structure. And then these air barriers as well, the fluid ones, as I mentioned, perfect for a wall like this where you've got a CMU or concrete, etc. And then again, we kind of mentioned as well, we'll get to vapor, I promise, because it is super fun as far as topics go. But each of these air barrier options are available in a vapor permeable, a vapor retarding, and a vapor barrier option. So we've got multiple options across the board. And then to kind of put that all together, this is showing a building under construction using basically these Rainscreen principles that we've kind of come to start to understand here. On the far left, you've got the yellow Dens glass board. That's our wall sheathing for the vertical as our wall cover board. And then you have your light gray material. That's a fluid applied air barrier. And then kind of as we move from left to the right, that light gray is also serving as our waterproofing drainage plane. And then on the right, we've got this light blue, that's extruded polystyrene insulation. So that's our continuous exterior insulation. And then to kind of complete this assembly, you're going to have your air cavity and then your cladding to be installed with hat channels right on top of that insulation. We looked at the perfect wall option where you had that kind of fairly common transition from wall to roof with the vapor barrier, or excuse me, the air barrier. But this detail here is taking into account vapor much more than that first one that we looked at. So this is a detail in which, let's say we're designing maybe a natatorium or even a gym sometimes, where essentially we need to account for the vapor control a little bit more because we have on the interior of this building either super high humidity, relatively speaking, like a pool would be, or say you have a museum or a data center where your tolerance for humidity inside the building is almost zero. We have to really keep it very controlled. This is what we're going to consider to be almost a special condition. In this case, we are going to suggest a high performance and active air barrier and vapor barrier. So air barrier that also serves as a vapor barrier on the inside face of the roofing insulation. So you can see that red line is what we're showing there. And for these types of buildings, you can't solely rely on the roofing insulation and the staggered joints of that double layered insulation to provide enough of an air barrier for these sensitive environments. Sometimes you can, if you don't have this really high humidity on the inside, but here we've got active air barrier on the inside face, maintained at room temperature, and are not going to be subject to condensation, which is really the whole point of having this kind of double layered barrier like this. But note, this wouldn't work everywhere. Again, high humidity on the inside here, but keep in mind, this is a situation where if you as the designer have concern or question, please consult a building envelope specialist or Garland. Obviously, we can help with that as well, but there are absolutely ways to detail this in order to facilitate that type of high humidity or kind of special condition environment. And this is just one of those examples, right? But that brings us into the much promised topic that I know everybody's been waiting for, and let's talk about vapor. So we've touched on it already, just in so much as we can have a vapor retarder to slow the flow of vapor. We can have a vapor open barrier, which will, or a vapor open sheet, I guess I should say, membrane that will just pretty much allow free movement of vapor from conditioned space to unconditioned space. Or you can have a stone cold vapor barrier that does not allow vapor to move at all. But the question that comes up pretty frequently still, do you always want to install the vapor barrier on the warm side of your insulation, considering it's winter? So that would be on the side that is facing or closest to the wall, right? The answer you might think is absolutely yes, but it's actually maybe sometimes, and it depends. Those three all mean the same thing in this case, but it also very much, not also, it primarily depends on where we're at in relation to our hygrothermal map, which is what we're looking at here. So especially when it comes to vapor, it's not a one size fits all. For us in Southern California, we do have a pretty kind of uniform hygrothermal region. And when we say hygrothermal, just to point this out as well, because I, prior to being with Garland, had no idea what that word meant. And I thought we were saying hydro, which is close but no cigar. A hygrothermal, just as a term, we're essentially talking about the propensity of condensation to propagate. So this is all about vapor, but I just always forget to kind of mention that because that isn't a term you hear every day, right? But for what we're working on out in Southern California, for the most part, we're in primarily zone 3 or region 3, a little bit in zone 2, sometimes into region 4 as well. But regardless of if we're in 2, 3, or 4, we are going to be more often than not, unless we have a special condition project like one we just looked at, we are going to be working with a class 3 vapor membrane, which for most of the time, it's going to be vapor permeable. Sometimes you will have a vapor retarder, but that will still allow 1 to 10 perms, which essentially is just the rate at which it allows the vapor and the condensation to escape the system. So good for us in that it's fairly quote unquote easy, you know, knock on wood, we're always going to be more often than not using that same type of vapor open membrane. But again, because it's not one size fits all and each project is different and each building has its own special conditions, right? It's important to know just kind of baseline what we're looking for when it comes to vapor barriers and what to consider when we place them within the wall system, where they are located within the system, etc. But essentially, we need to keep in mind water vapor is going to be present on both sides of our water resistant air barrier, both sides of our AWB. We need to ask ourselves, can both sides dry their respective space? Is drying improved by using both sides simultaneously to dry the vapor load? These are things to consider. Of course, when we are talking about only using a single layer of a vapor retarder, 2 vapor retarders within a wall or a roof assembly can trap moisture, which is kind of what we saw a little bit ago. Usually you're going to want 1. But in that special condition that we looked at, we had 2 different types, right? So that's like that indoor pool situation. But just principle-wise, warm air rises and air is going to want to move from a high pressure zone to a lower pressure zone. So that's essentially hot air to cold air. And in our case here, you know, usually in California, we're more focused on the air conditioning and cooling the buildings as opposed to, you know, in the Midwest and the Northeast, they're more focused on heating the inside of the building, which does change things as far as the equation is concerned, right? So something also that is a little different and kind of finicky about vapor, when we were talking about air leakage and the ideally lack thereof, you can't have a building that is too airtight, right? So redundancy in our air barrier is totally fine. This is different. Vapor is not the same, and it plays by slightly different rules, right? Some amount of discontinuity in the vapor control layer is usually tolerable. We're going to want to essentially make sure we have enough breathability so that we are not trapping condensation in any capacity. But again, that is something that when it comes to, if you're working on a building that has a really tight tolerance for essentially having no moisture or humidity inside the building at all, absolutely work with a building envelope specialist, et cetera, just to make sure that you're accounting for all factors, right? We will touch on this in just a bit as well as we get to the WUFI model too. That's all about vapor, which we can assist with as well. But let's talk about kind of our final layer here, which is thermal control. And this is all about insulation. And if you recall, all those minutes ago when we looked at the quote unquote perfect wall as compared to the commercial wall, and the perfect wall had the concrete structure, the commercial wall had that open stud cavity, and we very intentionally said that there was no insulation in the cavity. It is very common to see fiberglass bat insulation in the wall cavity. However, continuous insulation on the exterior side of your air barrier is bar none always going to be a more effective way to increase your R value and a more efficient way to increase your R value of your building. So we'll see a diagram in just a bit. It's a dew point diagram, which really shows this nicely, but it all is kind of coming down to the fact that when you have a steel stud cavity, those studs are absolutely acting as a thermal bridge, which is going to really kind of bring some vapor and condensation into play, but also reduces our energy efficiency of the system just in general. So having that continuous exterior insulation on the outside is huge. And there's there are several different options as far as what material is available for our continuous exterior insulation. One of them is mineral wool. And we say here it's the best choice. And that's taking into account a couple different factors. A really big one, especially that is top of mind out here, is the fire safety of it all. And mineral wool is NFPA 285 compliant, which is kind of the most important code when it comes to fire safety of buildings. Usually NFPA 285 is relevant for buildings that are 40 feet in height or taller. And in those cases, you would have to use mineral wool as your insulation above the 40 feet. When you are using mineral wool as your continuous exterior insulation, it essentially serves to negate that NFPA 285 code trigger because it is non-combustible and really doesn't have any, sort of issues with passing fire code, which is great. There are other options as far as materials are concerned. A polyiso can be NFPA 285 compliant, usually because that's essentially plastic. You have to have a very specific type or a very specific kind of face of that insulation in order to be code compliant. There's also extruded polystyrene. Same deal. Essentially, if you're using an insulation that is not mineral wool, chances are it's going to be some type of plastic. And we're seeing a couple of those options here. Of course, they all have different R values per inch, right? So we say that mineral wool is the best, just taking into account many different factors. It is important to note, though, it does have a slightly lower R value than polyiso does. And for sure, polyiso is definitely more prevalent, I would say, than mineral wool is currently. However, we are seeing a lot more mineral usage in Southern California. There absolutely also are some design firms that are essentially stipulating use of mineral wool only so that everything is NFPA 285 compliant, even if it doesn't have to be. So keep your eyes peeled for that. We're seeing that more and more. But really, mineral wool is essentially like spun stone fibers. So it's a natural fiber. It can be left out on the job site without losing its structural integrity prior to being, installed or prior to having the cladding installed. And polyiso doesn't have all of those same benefits. And this is that diagram that I had briefly mentioned a minute ago. This is that dew point diagram that is showing essentially the difference between what happens with a steel stud cavity with fiberglass batt insulation, which is on the right, versus a steel stud cavity with no fiberglass batt insulation, but continuous exterior insulation on the left. So on the left-hand side, you see the continuous insulation is keeping our air barrier, which is where that circle is right there. We've circled that point where the air kind of hits the inside controlled heated air, hits our air barrier / insulation at that point that is circled. And you can see we're keeping the air barrier at a temperature that is very close to the interior room temp. So this is winter. Exterior temp is like 5 degrees-ish. Interior temp, we're heated at a toasty 70 degrees. So the air from the inside, the hot, warm air is high pressure trying to move to low pressure. So it is essentially that air barrier becomes what is known as the first condensing surface, because that's where the warm air meets the cold air. So if you do have condensation, it will be right at this air barrier. Whereas on the right-hand side, same temperature situation, warm on the inside, cool on the outside. We have fiberglass batt insulation in this wall cavity and no continuous insulation on the outside of the air barrier. So what that means is, because that continuous exterior insulation is missing, the air barrier is not close to the same temperature as what we're seeing inside the building. So that warm air is traveling through this open steel stud cavity, through the fiberglass batt insulation, and hitting our air barrier at around looks like 14 degrees-ish before it kind of travels outside the system. So that point there is where the condensation occurs. Same as before, it's hitting that air barrier, but because the air has cooled down in that open wall cavity space through the fiberglass batt, that means we're going to have condensation within the wall system, as opposed to on the left-hand side where we don't have that condensation in the system at all. It's just right on the side of the air barrier there. But now we have the probability of and propensity for mold to propagate within that wall cavity, which is really kind of the whole point of trying to control our vapor and thermal entity as far as insulation is concerned. Again, it's all tied together. That would be not only damaging, if we've got mold in the interior of the wall cavity, health-wise and human safety-wise, not great. And also just dealing with that and mitigating that is, in a lot of cases, super difficult. And this is what we're showing here. This is like a real life example of this. This is actually an art museum, and you can see there is visible water kind of trickling down that wall. And really the only solution they had at this moment was to just have some buckets below, which is super pretty looking, right? Very unsightly. But not only that, it also is, it's kind of hard to tell just from looking at it. Like, is this a roof leak? Is this a wall leak? What are we working with here? This is condensation from the wall system itself that is just dripping down, ideally, hopefully not on any paintings. But before you can sort that out, this is a lot of times the only way to just solve, quote unquote, the issue before you can really get in the wall and see what's going on. And in the interest of time, we're going to skip a couple of these, or not skip, we're going to, zoom a little bit. But when it comes to thermal bridging and continuous exterior insulation, there are a couple schools of thought. In this particular example, we've got the thermal bridging that is essentially being caused by, we have a continuous Z that is attached right into our stud cavity, but that Z, because the metal is truly in between the layers of insulation, we are losing about 60% of our R value. So if you have a R10 that you're spec'd, your losing 60% of that, your effective R value in practice is about an R4. So we're trying to mitigate that. And this is one option to do so, which essentially we're like crisscrossing framing channels a bit and kind of crisscrossing our array and our orientation of the insulation, right? The thermal bridge is reduced only to the contact points where the metal framing layers intersect, which is reasonably effective. We have only lost 20% R value. However, this way of doing it is, you know, as you can kind of assume, I would think much more expensive than what we just looked at. And it just really makes the whole wall assembly a lot thicker, which is not always feasible depending on what the building is, which is why this now is definitely the recommended option as far as reduction of thermal bridging. So simple, highly effective. We're essentially fastening a furring channel or our hat channel, whatever we're working with, through the insulation. And the insulation itself is essentially acting as the thermal break. So the only bridging is caused by the screws, which is going to result in about a 5% loss of R value. So you are R10 nominal, we're higher than R9 effective rate, which is much better than what we just looked at. But by fastening this is our kind of support member for the cladding, by fastening that through the insulation into the structure, is this structurally sound? Short answer is yes. And I am more than happy to send this to you guys so you can really dig into the equations and with all of those exponents and all that really fun stuff that is, we're not going to get into it today, other than to say it will not affect the structure by attaching your furring through the insulation. The screws will not bend under the weight of a metal wall panel as you're cladding. Again, we're speaking in metal because that's kind of what we specialize in, but there is testing for this, and there also is some updated testing that will be available, I think actually next month. So it's been tested for up to 4-inch thick insulation, and more testing is coming out soon for up to 6 inches thick insulation as well. I can send this to you guys too, just so you see it. But really the point is, if you are designing a Rainscreen system that is functional and for a high efficient, high performing building envelope, usually if you're working with a very reputable manufacturer, they should be able to provide you with all of these types of details. Because as we really discussed, there are so many different factors at play when it comes to building science and efficient building envelopes, but a lot of it comes back to hygrothermal simulations, which is kind of how we're able to design a Rainscreen system that we know will work. Which brings me to my very last topic, which is a WUFI model. And I will not do WUFI the disservice of trying to pronounce what it actually stands for, but WUFI is an acronym. It's German for the organization that kind of developed this software, which is essentially, it's 3D modeling for propensity of hygrothermal activity within a system. So we can do this for any Rainscreen system in any area, but typically it is used for more of those sensitive situations. Like it can be used for museums, like a hall of records, where essentially what we're doing is we're dictating what the permeance of our vapor barrier or vapor retarder is that we are specifying. You put in your cladding, you put in truly a ton of project information as far as location, materials being used, etc. And we are able to run these models and simulations over years to verify that essentially if the system does take on moisture, which it always will, that it is able to dry out effectively, which is really what this particular example is showing. This is a pretty cut and dry example of system taking on moisture, drying out, moisture, drying out. This will perform great, no issues. We'll skip through this, but all you really need to know is some manufacturers can assist you with this. This one is an example of we have moisture that is accumulating. It is getting wet, drying out, we've got humidity, etc., up and down, but that line, the slope is gradually going up, which will over time be a problem. So we're going to need to adjust the permeability of our vapor open air barrier. This one is extremely excessive. These are just some examples, right, of truly what this system can do. It's very impressive, but please let us know if you guys need assistance with that. We're more than happy to run those WUFI models, and other manufacturers probably can as well. But again, now we're just gonna kind of round out the day or the hour with some photos. We've got a larger scale option here looking at that whole system. Just now that we know what each of these components are, I like to show this again, pre-cladding. But you can go as kind of quote unquote simple with the system as what we're seeing here, even though we do have several different transitions, and we've got masonry at the bottom, glazing, some nice kind of overlapping joints on the panels there, or you can get extremely creative and fun with it. This is a penguin museum where, you know, design intent was to look like an iceberg, and I think they nailed it. You can have kind of those, you know, you're not restricted to just rectangular panel shapes, even though that is a lot of what we see, right? So incorporating the standing seam roof into the wall panels as well, and having that kind of detail up top just transition that seam really nicely. Really, as far as renovation goes, a functioning Rainscreen is an awesome option, not only for a facelift visually, but also for an energy efficiency upgrade if you are incorporating that insulation into the system itself. But truly, aesthetically, the options are almost endless, and to have this be a functioning system that is also contributing to the performance of the building long term, it's truly best of both worlds. And we saw a lot of photos of metal. You can also do that system with a terracotta panel. Genuinely, as far as options go, you have so many possibilities. And I would be more than happy to discuss them further if anybody would like. Let me jump back on the camera real quick.
Yeah,
and I will
Alex, you do
see.
have a
Yes,
couple questions in chat.
perfect. Let me pull it up. Okay. Tom asked, SoCal climate for typical building types, not special conditions, what conditions can result in condensation on the inside of the air barrier? That's a great question. For typical building types, to be honest, Tom, we are not, especially in Southern California, per your question, we are not really seeing a ton of conditions that do result in condensation other than data centers, which, you know, sometimes you see cold storage facilities. You can see that sometimes as well. And then museums is one that we're gonna, you know, where anything where you have like a hall of records or a building that you have a really, you know, tight tolerance for protecting what's inside there. We'll see that occasionally, but great question. And then second question from Tom, what is the effect on air-water barrier from fastener penetration? That's a great question. There are some air barriers that are considered self-healing. Those are fairly common in the marketplace, where essentially if you are fastening the air barrier to your substrate, it will essentially have such a minimal effect, the penetration will, that it won't affect the functionality of the air barrier. However, I will say a self-adhering one usually will kind of be what we will recommend first. And if that's not an option, we'll make sure that it is detailed. The fasteners are detailed in such a way that we're minimizing any sort of, you know, punctures where air can leak out. But if you also are factoring in insulation too, a lot of the time insulation will act as a vapor barrier in a lot of cases, and an air barrier sometimes too. So you'll have a little bit of redundancy there. But great question. And then final question, asked for a copy of the presentation. Absolutely, Baram. I can send this out to whoever would like it. And then I also have I left my contact info up on that slide that is still showing, but I think Marilee also included my contact info in the reminder email too. So if you guys do have additional or kind of more specific, project specific questions, please don't hesitate to reach out. Thank you guys.